So now the final task of the assembler is to go through the instructions, and for each instruction actually figure out what the exact bit pattern is that we need to program into the program memory to encode this instruction. And we've used to do this manually. If you recall in this ISA.txt file, we went through all of the instructions and wrote up this hexadecimal representation for it. And this was a pretty tedious task. So I think this is the final thing we really want to automate with this assembler. And so similarly to how we dealt with the addresses in the instruction, with the address being an optional field, I think we want to have an optional encoding field on the instruction where we can store the exact way how the instruction needs to be in the binary. And it's just going to be exactly the same as the address. And then in the assembly printer, we want to do the same thing as we did for the addresses. If there's encoding information in the program somewhere, we actually want to include it in this assembly dump here, such that we can inspect what the assembler is doing. So same here, instead of emit address, we have an emit encoding field. And if any of the encoding fields of the instructions are set, we're going to set this emit encoding flag. And then for each instruction as we print it, if this emit encoding flag is set, we actually want to print the encoding. So let's start out with maybe an empty string by default. And the encoding is going to be 2 bytes. So that's 4 hexadecimal digits, 1, 2, 3, 4. And then if there's actual encoding information, we want to use that instead. Like this. And then finally, we just want to prefix the instruction with its encoding. All right, let's see what happens. Theoretically, nothing should change because none of the instructions have any encoding information. That's exactly what happens. But now let's change the last instruction and let's give it some random encoding. Cool, that seems to have worked. So the last instruction has some encoding information, and so it gets this hex F142 printed as its encoding. But again, instead of doing this manually here by just writing into the encoding field, I think we want to have an instruction encoder class that goes through the program, goes through every instruction, and just takes the operands and the opcode and does its magic and just creates these 2 encoding bytes that we need per instruction. So we'll use the exact same pattern, create an encoder, ask it to encode the program, and then we pass it the program to encode. So let's go write this thing. All right, and so this thing needs an encode program function. And what we want to do is just go through every instruction in the program and encode it. And now, how do we actually encode the instructions? I think what we want to do is store the current instruction in a variable of the encoder, so we kind of know the context of what we're currently encoding. And we want to create an encoding variable, which just holds the bits that we've assembled thus far for the current instruction. And this will also help us to create some useful error messages, because we know what the current instruction is, and so what the context is. So let's create an error helper here that makes use of this information. And so all this does is it takes the message and adds the current instruction and then calls the regular error handler. And so as a first step, what we can do, because we don't know how to encode instructions yet, we can just error out and indicate that we don't know how to encode this instruction. And then finally, at the end of the function, even though we can get there right now, we just want to store the encoding in the instruction. So let's see what happens if we run this. Pretty cool. So we're calling this instruction encoder all the way down here, and it goes through the program, and then in the first instruction it actually complains that it doesn't know how to encode the instruction. It says unencodable instruction, and it shows us that it's talking about the LDI instruction. Let's actually start out with the NOP instruction because that's easier to encode, and let's insert one at the beginning. So all the way at the top, instead of a load immediate, we'll have a NOP. And so it's complaining about the NOP instruction. And so let's think about how we can encode this. And I think we'll want an encode bits function that just allows us to write a certain bit pattern. And for NOP, this is pretty simple because we want to set all 16 bits starting at bit 0 to the hex value 0. Now it's going to complain that there's no encode bits function, so let's write that up. So this is our bit encoding helper function. We want to take this value here and we want to store it at the bit range starting at offset with the length. And so let's first check a few invariants. First of all, offset cannot be negative. The length also can't be negative. We can't write outside of the 16 instruction bits. The value must be positive. And the value must fit into the number of bits that we are actually assigning. And this is going to help us find errors in our code. So first of all, we want to clear the bits in the instruction that we're selecting to 0. This is the usual trick of creating a binary number that has the lower length bits set to a 1. And then we are shifting this to the left to the starting offset. And this basically creates a mask where everything is 0 except for the bits starting at offset, offset plus 1, offset plus 2, etc., until offset plus length minus 1. So all the way up to the length we have selected. And then here, what we're doing is we're taking that mask, we're inverting it such that the bits that we're interested in are 0 and all the others are 1. And then we're ANDing this onto the encoding. And the AND operator is basically whenever the mask is a 0, it's going to clear the instruction bits to 0. And whenever the mask is a 1, it's going to leave the instruction bits untouched. So this, in essence, clears out the bits we're selecting here. And then as a second step, all we need to do is just take the value, shift it up to the offset, and then OR it onto the encoding. All right, so that should allow us to encode bits pretty efficiently. And this seems to work. We have skipped over the NOP instruction and we have encoded it. And we're now at the load immediate instruction. And we don't know how to encode this at the moment. So let's look into that. Up here, let's create a branch for the LDI instruction. So the load immediate, if we check the ISA specification, load immediate has the lower 4 bits set to the value 8. So what we can do is we can say encode bits from 0 to 4, so the lower 4 bits, and please put a hex 8 in there. But on top of that, we also need to encode the different operands that we have. The load immediate, it has the RD operand, which is in bits 4 to 8. And it also has the 8-bit immediate value here, which is in bits 8 to 15. So let's encode these as well. And I think we want a helper function for that because all of the instructions are going to have some form of these operands. So we're creating 2 new functions, encode RD, which is basically taking an operand and it's encoding that operand as the RD operand of the instruction, so the destination register. And encode immediate 8 is taking an operand and it's encoding it into the 8-bit immediate field of an instruction, which is this field here. And so when we're encoding an operand as a register RD, let's first make sure that it is a register operand, not some immediate for some reason, and that the register index is actually supported by the CPU. So this will print an error message if the register operand is illegal. And then afterwards, once we're sure that the operand that we have is actually a register, we can actually store the register index into the instruction. And if we check the ISA here, the RD operand is bits 4, 5, 6, and 7. So it's the 4 bits starting at bit offset 4. So that's exactly what we're doing here. Starting at bit 4, we encode the 4 bits from there. And we're storing in there the register number plus 1, such that R0 is stored as a 1, R3 is stored as a 4, and 0 is reserved for indicating no register operand. Next up, we also have this encode immediate 8 function that we need. And so what we want to do here is we want to make sure that the immediate value is actually in a range that we can represent in the instruction. So it should be at least minus 128, because that's the smallest signed 8-bit integer that we can have. And it should be below 256, because that's the largest 8-bit unsigned value that we can have. And after that, after we're sure that the immediate is actually going to fit into the instruction, we can encode it. Starting at bit 8, we are going to set the next 8-bit in the instruction, so that's the upper 8 bits, and we're going to set it to the operand value, which is just going to be the immediate value. And we're doing a AND operation with hex FF, which is just a trick in Python to make sure that if this is a negative number, it actually gets converted into a 2's complement number, which we can actually encode into the instruction. So let's go and write this check immediate function. So first, a general error if we were given a non-immediate operand, like a register or some other thing we cook up in the future. And as a second step, we're checking if the value is actually below the lower bound, or if the value is above or equal to the upper bound. And if that's the case, we're going to show an error message and indicate to the user that something went wrong here. Let's actually add some comments here. All right, and let's give this a shot. Nice, that seems to have worked. So we're now past the LDI instruction, and we're now at the move instruction. And one thing we can do is we can actually print the instructions as they are encoded, so we can see if we're making any progress here. And yeah, that actually looks pretty good. So if we compare this to our test program, we have encoded the NOP instruction as a all zeros value, and the LDI instruction that loads the 0 value into register R0 as the hex value 0018. And if we compare this with our old program, which we manually assembled, this actually lines up. So the 8 here is indicating that this is a load immediate, and the 1 encodes register R0. And then the 00 up here is just the immediate operand here. And so if I go in and I change this, you can actually see that the encoding changes. We're now writing into register address 4, which is R3, and we're writing this hex 55 value, which is the 85 here, the hex 55 that we had here. So that seems to be working. Let's move on to the move instruction. Move is similar, but if we check the encodings here, move has a 0 in the lower 4 bits. So we are going to write a 0 into the lower 4 bits, and then we're going to encode the RD field with the first operand. And now move also has an RS field, which is the source register, and we're going to encode the second operand there. And so we need an encode RS function here, which is going to look almost the same. Going to do the exact same checks here, with the sole difference that the RS field is at offset 8 in the instruction. And then here we also want to mention that this is an RS register. And then let's see if this works. Pretty cool. Let's compare against the manually assembled version. And as you can see, this actually seems to line up. We have a 12, 23, 34, 45. And as you can see, this matches the program that we manually assembled. All right, next up is the jump relative with immediate. Let's go check the encoding for that. Jump relative with immediate. The encoding is a 09 in the lower 8 bits. So in the lower 8 bits, we are going to write a 09. And since the jump relative with immediate instruction takes a signed 8-bit value as the jump offset, which can range from minus 128 to plus 127, we want to create a new encode function for it specifically for these signed immediates. So let's go implement that. It's actually pretty much the same as the regular immediate 8 encoding, but we're just making sure that we're not writing a too large value into this field. So let's see if this works. Okay, seems to have gone and encoded the instruction. Let's check against the manually encoded one. 1209 is indeed correct. All right, next up is a directive, and I think we just want to ignore directives. Okay, that worked. We're skipping over the directive, and so next up is a jump relative with register. And if we're going to check in the ISA file here, jump relative with register has a 0, 1 in the lower 8 bits. So that's what we're going to put there. And then it takes a regular register as its RS operand. And there we go, jump relative with register has been encoded. Let's check if it's correct. Jump relative with register, it's a 0101, and that's exactly how we encoded it. Cool. And so the final thing left is jump absolute with register. And it's actually going to work almost the same as the jump relative with register. So it's jump absolute with register. The encoding for jump absolute with register is a 02 in the lower 8 bits. So we're going to write a 02 there. And we're now encoding not just an RS operand, but an RS16 operand here. And so RS16 is basically just indicating that this takes a register pair. And so let's create some encoding logic for that. Let's duplicate what we have here. And so we're going to check that this is indeed a register pair. Because we're pairing up the register indicated by operand value plus the next register, we have to make sure that the next register also exists. But the encoding is actually exactly identical to the regular RS operands. It's just that the validation here is slightly different. And that seemed to have worked. Jump absolute with register has been encoded as 0102. And if we go check here, 0102 is the encoding we also came up with manually. Now there's this HALT instruction, which we didn't have in the original code, but we have here. And HALT is pretty simple. HALT is just a pseudo instruction defined as all 16 bits of the instruction set to 0009. Let's create a pseudo instruction for HALT. And we're just going to encode the bits 0009. And that seemed to have worked. The HALT was encoded as a 0009. And then the remaining instructions of the program got properly encoded. That is pretty cool. Now I think there's a small amount of cleanup here that we can do to make this encode instruction a bit easier and make it align more with how we handled the printing, where we had some code that handled the instruction and we could just return out of the current instruction. So let's do this here as well. Let's do all the pre-processing here. Let's move this into the program encoding. Let's move this part here also into the program encoding, like so. Probably don't need the printing anymore. And then here we can change this around a bit. That's actual instructions. Then we have the pseudo instructions. And then we have the directives. In this case, we want to clear the encoding to none, so we don't actually store an encoding here. And then otherwise, we just complain about unencodable instruction. All right, forgot to change this around. All right, that seems to be working. Pretty cool. Now, one thing we should try is to see if we can actually make these checks fail. Currently, we don't really have a way to parse in a register that kind of violates these constraints, so there's not much in the way of how we can test that. But the immediate values, they are the typical case where something goes wrong, and we can actually test that. So let's say we want to load a value into R1 which is too big. Let's see what happens. Cool, so we actually get an error message indicating that this immediate value here that we typed, which apparently was 3840 in decimal, is too big, it's out of bounds, and we have to make sure that it is within minus 128 or just below 256. And similarly for the jumps, if we make this jump too large, for example 180, remember we can only jump forward by up to 127. We actually get an error message that this doesn't fit. Cool, so that actually seems to work. This is pretty useful. Another thing we can do in the printer for the emission of the jump relative with immediate instruction here is if there's some addressing information available and we know where in the binary this jump relative with immediate instruction is, we can actually compute the address that this is going to jump to, and we can print it as a comment at the end of the line here. So let's see if this works. And if we scroll up, yeah, sure enough, this actually shows us where we're going to jump to, which is pretty useful. All right, so that's quite a large chunk of the work done. We can parse the input assembly files. We can compute the layout of the instructions, basically computing where they are in the final binary. We can encode the instructions, which is figuring out what the exact bit pattern is that the CPU needs to execute them. And we have a method to print it back out as an assembly listing with additional information, with the addresses of the individual instructions, plus the actual encoding of the individual instructions, which is pretty useful and quite neat. And so I think all that's left to do now is basically take all of these encoding bits here and concatenate them into one big blob of bytes that we can write to disk into a file, and then this can go and be written into a program memory. So I can't wait to tackle that finally. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.